Okay, I think we can start. I hope everybody hears me well. So, hello, my name is Karolina Prawda. I will be chairing this session, and welcome everybody to the first session of our NordicSMC conference, which will be in the topic of physical modeling. And we have some presentations. We have 4 presentations in this session. So we will start with applied physical modeling for sound synthesis, the Yai Bahar by Pelle Juul Christensen, Sylvin Willemsen, and Stefania Serafin. Then a Faust implementation of coupled finite difference schemes by David Südholt, Riccardo Russo, and Stefania Serafin, followed by a real-time interactive physical model of the Langeleik using finite difference schemes and web audio by David Südholt, Søren Lyster, Oliver Winkel, and Stefania Serafin. And then the last presentation of the session will be the real-time implementation of nonlinear physical models with modal synthesis and performance analysis by Alessandro Cerioli, Michele Duczewski, and Stefania Serafin. Sorry if I mispronounced any names, but I think we can start now.
Thank you for the introduction, Carolina. We're ready to start, so Sylvan's going to play back the presentation videos, and let's go.
Hello, my name is Pelle, and in this video I'm going to talk about our project, Applied Physical Modeling for Sound Synthesis, the Yai Bahar, that I made in collaboration with Sylvin Willemsen and Stefania Serafin, and we are all from Aalborg University in Copenhagen. So the Yai Bahar is an acoustical instrument invented by Turkish artist Görkem Sen, and it consists of a string connected to 2 springs connected to 2 drum membranes, and it sounds something like this. Okay, so you can hear that it has this huge reverberant sound and that it can be played by bowing the string or by striking the drum membranes or the springs. So we wanted to recreate this sound digitally, and the method we chose to do so is finite different time domain methods. And in this method you describe your system as a differential equation, you then discretize that equation, and you then implement it as software so that you may solve it numerically. And a really good resource for this topic is Numerical Sound Synthesis by Stefan Bilbao, which is also where you will find most of the sub-models used in this project. So the first part of the instrument is the string, and this is the differential equation that describes the dynamics of the string. So what this says is that the acceleration of some point along the string is equal to all the forces described by the terms over here on the right hand side. So the first force acting on the string is a restoring force that is due to the tension of the string. So if you have like a displacement of the string, the tension is going to try and pull the string tight. And this integral in here makes it so that the more displaced the string is, the tighter it will be and thus have a stronger restoring force. And this makes the string nonlinear. The next term here is the restoring force due to the stiffness of the string material. So if you have a stiff material and you displace it, it is gonna wanna spring back again. And this term describes that behavior. Next we have a couple of terms that deal with damping, and the second term here implements frequency-dependent damping, so that higher frequency partials die out faster than lower frequency ones. And lastly, we have external forces acting upon the string. So to turn this differential equation into a finite difference scheme, we take each of the derivatives in here and we replace those with so-called finite difference operators. And these operators are approximations, they are discrete approximations to the derivatives. And yeah, the entire point of this technique is to choose the right approximations for all of your derivatives. And once we have found a nice scheme for our equation, we will expand all the operators that deal with time. And from there, we can shuffle things around using simple arithmetic, and we can arrive at an update rule. And this update rule will say that the state of our system at the next time step can be computed from the current and the previous time step. And if we do this recursively, we can run a simulation of the string and produce sound. Moving on, the next part of this instrument is the spring, and this is the differential equation for the spring, and it says that some point along the spring is equal to the forces over here. You see that unlike the spring has no tension, and that is because the spring is not under tension, and the only restoring force is the stiffness that you see here. It's exactly the same as before, and then we have the same damping terms and external forces. Now the last part of our instrument is the drums. Yeah, the two drums. And these are a bit more tricky because whereas the string and the spring are both 1D systems, the drums are 2D systems. So that makes stuff a little bit harder, but actually the equation looks very much the same as for the string, and the only restoring force is the tension. We assume that the drum membranes are made of some non-stiff material like plastic or hide, and that is why there is no restoring force due to stiffness. And again, we have damping and external forces. Now that we have all our different elements, we need some way to connect them. And we do that by computing a force acting like between the two elements, for example, between the string and the spring. And that is computed simply by the difference between the two of them times some constant. Now in the video we saw Görkem Sen playing the instrument with a bow, and a bow works by the friction between the hairs of the bow and the string. So the bow is going to pull the string along until the restoring force in the string becomes so great that the string will shoot back only to be caught again. And that gives us this periodic motion. That is how a stringed instrument sounds. And this friction is simulated by this function phi, that is a function of the relative velocity between the bow and the string. So an important topic when dealing with these finite difference schemes is that they are not inherently stable. And the stability of your system is going to depend on how you discretized your equation and your choice of parameters. And normally we will derive a stability condition, that is a mathematical expression that tells us how to choose our parameters so that our scheme is guaranteed stable. This can be pretty tricky for nonlinear models such as the ones we're using. So what we did is that we used the stability conditions that are known for the linear counterparts of the systems that we're using, and then we added a bit of headroom so that to account for the non-linearity in the systems that we're using. Okay, enough math. Let's hear how it actually sounds when we run these models. So here you see the C++ application that implements our models, and we have the two drums, we have the springs, and we have the bowed string. I can strike the drums. I can also strike the springs. And if I apply a bit of bowing force, I can start the string oscillating.
Hello and welcome. I will now be presenting a Faust implementation of coupled finite difference schemes by David Süthold, Riccardo Russo, and Stefania Serafin. We'll first talk about what we actually mean when we say coupled finite difference schemes. Finite difference schemes, or FDS, are a method of physical modeling where we take a set of equations that describe the physical behavior of an instrument, and we approximate a solution to these equations by discretizing time and space. We're talking about one-dimensional FDS, a guitar string, for example. But when we take a look at a real guitar, the string isn't just vibrating in isolation. The oscillations are transferred to a bridge, and from the bridge to the other strings and the body. So not only do these other parts then vibrate on their own and produce a sound, their vibrations also are transferred back to the originally plucked string and affect its oscillation. So we can have a small look here at a simulation of such an FDS of 3 strings that are connected to a bridge. The strings are connected to the bridge here via a rigid connection at the points on the bridge that are indicated here, and the bridge is connected to the strings at the black dots. And we're going to plug string 1 and then see how the vibration is first transferred to the bridge and then from the bridge to the other strings. So the other strings begin to vibrate, although it's about an order of magnitude smaller, and their oscillations are then transferred also back to the bridge and back to the originally plugged string. And so it's a complete system that affects each other if we want to, as faithfully as possible, model a complete guitar. If we look at a general coupled system then, if we look at the math behind it, we're looking at m different systems that each of them have an update equation for a discrete grid. So this is just some normalizing factor times a state q, and this state q is a linear combination of a grid point's neighbors in time and space. This neighborhood is called the stencil, and it's illustrated here, where the next value for this grid point here in red depends on its neighbors in time backwards, so each row represents a time step, but it also depends on some spatial neighbors, and so this whole neighborhood in total is called the stencil, and Q is calculated as a linear combination of each of these grid points. If we now want to allow arbitrary couplings, we define a coupling as a tuple that consists of the 2 indices of the systems that we want to couple together, which are here R and S, and the locations on the system where we actually want the coupling to be. So we need one position on the string, for example, and one position on the bridge, where these 2 are then coupled together. We then extend the update equation, this update equation here, by including the forces. So we still calculate the intermediate states as before, but now we also need to calculate connection forces and add them to the schemes where the scheme is the coupling above the other one, and subtract them from the couplings where the coupling is the below part. So the spreading operator J here takes care of applying the force to the correct grid points, and then the whole thing is, as before, normalized by some factor. So the only thing that we actually need to know here is how to calculate the force. And there's a few different ways to do this based on the nature of the connection that we're employing. Currently, we're just assuming rigid connections here, and that leads to a fairly simple explicit formulation that just depends on the intermediate states Q. So now we're looking at how we can use this formulation in Faust. Faust is a functional language, which means that common data structures one would typically use to represent the grid that you saw earlier are not available. Instead, everything is a stream of signals. So in the Faust FDS library, every part of the FDS, like the coefficients for the update equation, the force input, and the current grid value, all of that is represented as a signal stream. And the magic happens in how these signals are routed and combined into each other. So here we see how a single grid point calculates the value for the next time step based on an input of an external force, the scheme coefficients, and the neighboring values. And we see that the routing distributes the current grid values, pairs them up with the coefficients, and for the coefficients for the previous time step internally in this operation block, appropriate delay is applied, and then the output of that whole block is the next state of this single point in the grid at the next time step. So we can then stack multiple of these to obtain a grid, in this case with just 3 points. And the output values, all of the 3 output values of these grid points are fed back into the whole scheme using Faust's feedback operator. And all of these grid points have their own sets of coefficients, which are mostly going to be the same for most scheme points, but in particular we can modify them at the edges of the grid to modify the behavior for the boundary conditions. So far this is all part of the FDS library that is already in Faust, but now we're going to look at System 1D, which actually implements the coupling mechanism that we discussed earlier. So we can stack multiple schemes on top of each other, which in Faust just happens through parallel composition. And then we use the existing Faust FDS library function to calculate the intermediate state Q. So this is just pairing the coefficients up and like applying the appropriate delays and just updating each scheme individually to get these intermediate states here. Then we feed these states into the force update calculation because that depends on the values Q. We calculate the force and apply it, and then finally this goes through the normalization by this factor A, and then the grid values, all of the grid values are fed back into the system as before, and we still have an external force input, which might be plucking the string, for example. Calculating the coupling force is divided into an interpolation, a calculation, and a spreading step. So we get the intermediate values Q in here, and in this example here we use linear interpolation. So the 2 grid points that surround the point where we defined the coupling to be are reduced into a single value. This single value is used to calculate the force, and then this force is spread back onto these grid points. It would also be possible to use other forms of interpolations, for example, cubic interpolation, and then we would have more than 2 grid points that affect each of the single couplings. We're going to have a quick look at the demonstration. So the code for this is linked in the paper, and we can simply run it in the Faust online IDE. And I'll briefly demonstrate then how this mechanism works. So this example here is 3 strings coupled on a bridge, and we have 0 to 3. The scheme 0, 1, and 2 represent the strings, and scheme 3 represents the bridge. And we can set where we apply the input, which is just plucking a string. We can set how hard we want to pluck and where we want to listen, and specifically which scheme we want to listen to. Right now we're listening to the first string, and I will simply pluck the first string. So right now we just heard the first string plucked at the first string. We can also do that, like move the output and pluck the second string, and we will hear the second string being plucked. We can also slightly hear the ringing, and this is going to be more clear when I switch the output back to the first string, but actually excite the second string. And now we can faintly hear the ringing, that is the resonance transmitted from the second string over the bridge to the first string. This is a bit clearer if I turn up the force by a lot. Listen to the second string and excite the first string. Then we clearly can hear the ringing that is transmitted through the bridge. We can also excite the bridge and simply hear the resonance of the second string. Okay, so yes, we use the Faust FDS library to implement a coupling mechanism. It's limited to rigid connections and 1D schemes right now, so there's definitely some room for generalization. And when it comes to performance, this is right now a bit hard to put into numbers because Faust can compile to a number of different backends that can vary greatly. So it can compile to C++, it can compile to other high-level languages such as Soul, it can compile to JavaScript. So these are vastly different backends also in terms of their performances. And then the Faust compiler itself has a few different optimization options. So it's definitely worth looking into how this stacks up in terms of performance, but because there is no sensible one way to compare speed, this is outside of the scope of the current paper and will be left for future work. So thank you for your attention so far, and I'm looking forward to your questions. Hello and welcome. I will now be presenting a real-time interactive physical model of the Langeleik using finite difference schemes and web audio by David Sütterl, Søren Lister, Oliver Winkel, and Stefania Serafin. So we'll start out with a small excerpt from a Langeleik performance. So the Langeleik is a traditional folk instrument in various northern European countries, but today it's mostly associated with Norway, where they're being built and played to this day. There is a single fretted melody string and a number of drone strings that can vary a bit from model to model, but usually it's between 5 and 8 strings. It's played by strumming a rhythm on all strings with one hand and then using hammer-ons and pull-offs on the melody string. So our model was created with the technique called finite difference schemes, so FDS. So that means we describe the instrument behavior with partial differential equations, and then we discretize space and time and approximate a solution by simulating the system time step by time step. This is a bit more computationally demanding than other methods, such as digital waveguides, for example. But it offers a great amount of flexibility and a close correspondence between model parameters and the actual physical characteristics of the instruments. Because of the computational demands, real-time applications using this technique are often written in compiled languages like C++, but the resulting application from this needs to be built for the user system, and they need to download and execute it locally. So since the general idea here was to increase the exposure of this traditional instrument, it would be valuable to reduce the friction and create a web application that just runs in a browser, and we will use the JavaScript web audio framework to implement that. So let's take a look at the interactions that we need to realize. One of them is strumming various strings. If we want to pluck a single string, one way to model that is to apply increasing force to a single point on the string and release it when it reached some maximum force. So this can, for example, be expressed by this inverted cosine, and we have a visualization of what applying that looks like. So increasing the force, then suddenly it's released, and then the string starts to vibrate, and yeah, we have plucked the string. And then strumming the strings is just plucking all of them basically at the same time, so just or like near simultaneously. On the melody string, it gets a bit more involved since we need to model hammer-ons, fretting and pull-offs. And what we did was we represented each fret as a finger, and all of the fingers are initially above the string in the bass state, and when the user presses a single fret, we start to accelerate the finger downward to collide with the string at some externally defined velocity. Once the finger actually hits the string, the tension of the string will be pushing the finger back upwards. So we need to account for that and increase the applied force to keep the velocity roughly constant. And then once the finger reaches a defined position somewhere below the string, we keep it just stationary there. And while it's there, it will act as a fret and shorten the string. So while the finger is pressed down, we will get a higher pitch from the string. And then when the fret is released, we basically teleport the finger back to its starting position. And this instant release acts as a pull-off excitation. And to model the collisions between the finger mass and the string, we use the methods to solve nonlinear collisions non-iteratively to actually be able to do it in real time that Duchesky and Bilbao presented in their 2019 paper. We also have a visualization of what that looks like here. So we have the hammer-on excitation here, and we can see that the finger is, while it's pressed down, acts as a fret. We have a second hammer-on, and the string is shortened even more. And then the second hammer-on will be released shortly. Yes, there's the pull-off excitation, and we're back to the pitch that we get by just pressing that first finger down. So then we move to the implementation of the web application. As we mentioned, we're using the JavaScript Web Audio Framework here, and the FDS processing is handled by custom processing nodes. Web audio nodes take in a signal of a fixed length of 128 samples as input and produce 128 samples of output. For our purposes, we interpret the input that the node gets as a force signal for the plugging, and then we output the audio that the FDS algorithm generated. So here's a processing graph of the entire architecture. So on the left, we first see the buffer sources that are generated and filled with a force signal whenever a user presses a fret. And they're then routed into the string processing nodes, and we can see that each of them has an individual gain control. The string signals are merged into a single audio signal, and then to that audio signal, convolution reverb is applied to simulate the resonance of the body. So we have an impulse response for a body that we generated in advance, and then we just use convolution reverb in the real-time application to have the body resonance. Yeah, and then we basically have our output, some gain and like being able to turn it off and on, and that is the node architecture. For the interface, we roughly wanted it to be played similar to the real instrument. So you use one hand for fretting, that's on the keyboard for our application, and one hand for strumming, which here is done with a mouse or touchpad. Where and how fast you strum affects the sound, and there's some visual feedback to the actions. So we will take a look at a demonstration now. There are 2 octaves of frets that can be pressed by using the indicated keys on the computer keyboard. Pressing a fret results in a hammer-on excitation, releasing it acts as a pull-off. While the fret is pressed, the pitch of the melody string is changed accordingly. Multiple frets can be pressed at the same time to change the pitch of the pull-off. So we demonstrated that it's possible to implement a real-time FDS instrument model on the web. It would be nice to extend the support so that it works better on non-Chromium based browsers and also maybe mobile platforms. And definitely the interface design needs some more iterations to be actually like more intuitive and to make it easier to actually use the model musically. Yes, so that's it for the presentation. Thank you for your attention, and I'm looking forward to your questions.
The current work consists in a C++ plugin developed with Juice framework for the physical modeling simulation of different systems in real time. In particular, the model synthesis was used to simulate the behavior of three models: the string-string model, where two stiff strings are connected, the plate-plate model, where two plates are connected, and the string-plate model, where a stiff string is connected to a plate. The components of the different models are connected together in a nonlinear way by means of a spring. Here is reported a brief introduction concerning how to use such VST3 into the context of a digital audio workstation. In this case, Reaper was used. The A panel is useful to select the model to play. As previously mentioned, here are three different models available: the string-string model, the plate-plate model, and the string-plate model. Finally, a further option called No model is considered to play directly the input signal, or rather the excitation of the system. The B panel is associated to the model currently selected, in this case the string-plate model. As a result, there are all the parameters which could be directly manipulated by the user, such as the frequency-dependent damping, the frequency-independent damping, the radius of the string, and the point of excitation over both the string and the plate. The C panel is addressed to the selection of the type of excitation to apply to the system. There are 5 different types of excitations: the sine wave, the square wave, the sawtooth wave, the triangle wave, and the raised cosine. The first 4 types are waveforms, and consequently they present a pitch. For this reason, with such excitations, the system is used as a resonator and the pitch of the outcome is the same as the pitch of the incoming waveform. Conversely, the raised cosine function is an impulse-like excitation, therefore without a pitch. In this case, the system is used as an instrument, and the pitch is defined by the parameters of the model. With the D panel, it is possible to manipulate the attack, the decay, the sustain, and the release of an envelope applied to the input waveforms. The E panel presents 2 sliders. The input slider is useful to manipulate the intensity of the input's excitation. Instead, the gain slider can be used to manually normalize the output signal. As a matter of fact, such models based on discretization present output signals of different magnitudes, which could be hardly algorithmically defined a priori. The F panel is a text box containing all the parameters associated to the model, also the ones whose cannot be directly changed by the user through sliders and knobs. The G panel is a keyboard which shows which are the allowed notes and which are the ones currently active. With the No model option, it is possible to play directly the input excitations, and the ADSR sliders can be used as envelope for the waveforms. As previously mentioned, the models proposed in the current work are 3. The string-string model, where 2 stiff strings are connected by means of a spring, the plate-plate model, where 2 plates are connected by means of a spring, and finally the string-plate model, where a stiff string and a plate are connected through a spring. They all can be used as resonators when a waveform is used as input excitation, or as an instrument when a raised cosine function is used as input excitation. Now, all the models are presented both as resonator and as instrument. Physical modeling synthesis is well known for the realism of the sound, but also for the high amount of computation necessary. For this reason, here an analysis of the performance was carried out in order to define the limits with which it is possible to use these models in real-time applications. A correlation between the size of the system, given by the number of modes used, and the CPU usage required was analyzed. It is easy to notice that there is a direct linear correlation in the range between 0 and 1200 modes. As a matter of fact, the black line represents the actual relation between the size of the system and the CPU usage required, while the blue line represents the linear regression. An analysis concerning the CHORDS was carried out as well. We can notice that the CPU usage required is strongly affected by two factors. The first is the register of the chord. In fact, the lower notes require a higher number of modes and, consequently, a higher CPU usage to be represented. The other factor is the type of the model. In fact, the plate is a b-dimensional physical object which requires much more computation than the string, which is a simply one-dimensional physical object. As a result, the stripped string can be used to play polyphonic music in real time, while the plate is strongly recommended for monophonic music. Finally, we can state that with nowadays computers, it is possible to make physical modeling synthesis based on numerical solutions in real time. Now we know that there is a linear correlation between the dimension of the system and the CPU usage required. Consequently, we can estimate if a given model can be played effectively in real time. Finally, here, nonlinear connections in model synthesis were introduced to connect isolated systems into coupled systems.
All right, so thank you everybody for presenting or recording your videos, and the audience for listening. And now we'll have our Q&A session. So I would kindly ask all the presenters to turn on their cameras so we can see you as well as here. Is that everybody? Is Pelle here? I don't know if I see him.
No, it appears we've lost Pelle, but while we try to get him back, if there are questions for the other authors, we can start with those. Oh, Pelle is here. Okay. Just a moment.
All right, so let's maybe then start with questions to the other authors, or maybe Pelle is here, but let's come back to him later. So first, maybe a question to David. So about your Faust implementation, have you tried what are the, let's say, boundaries of that system? Have you tried like whether you could, what number of strings you could put in that so that it still works? Can you make like very unreal instruments with that system, or is it quite limited? How would you say?
There is sort of a general limitation inherently to the Faust FDS system, because at a certain point, when there are too many grid points in the system, just generally the compiler starts to run out of memory. But this is more inherent to Faust in general. I personally have noticed that happening with either like anything north of 10 strings, or any kind of two-dimensional plates that have like more than around, let's say, 60 by 60 or something at the grid points. But yes, I've also like tried using this particular system, like the connection system with 10 strings, and haven't seen any problems with that. So like there is this kind of like hard limit of Faust FDS in general, but up to that limit, the coupling mechanism works fine.
Okay. Thank you so much for that answer. And we have a question for Pelle. So Pelle, you said that you use the linear stability condition for the nonlinear string, but you left some headroom for nonlinearities. How did you deal with instability that may come from large amplitude vibrations?
So what I mean by headroom is that when we get these large amplitude vibrations, I have like added a bit of headroom to the stability condition so that like the resulting tension, for example, that will be due to this large amplitude, because of the headroom, the system will still be in the stability condition of the linear system, right? So if the parameters of the system, they switches by like 10%, I have added 10% headroom, so to account for this change in parameters due to the nonlinearity.
All right, thanks for the answer. And I have one more question for you. Have you in any way somehow evaluated how close you are to the original instrument? Do you have that instrument, or have you like tried with some type of subjective or objective evaluation whether it sounds, whether you can fool the listener with your model?
No, I haven't tried anything like that. I think it would be quite hard with this models still to convince anybody that it's the same as the real thing. But this is more thought of as an exercise in like analyzing and modeling an instrument, and also in utilizing these nonlinear resonators that I don't feel you see as often in the literature on this topic.
All right, thanks so much for the answer. And I have one question that can be, first maybe Pelle can answer, and then David, since you both had quite, I would say, unusual instruments modeled in your work. So can you elaborate a bit on why those instruments are there interesting for you? Was it some more of a random choice? Like what was the decision behind modeling those instruments that you used?
So the reason I chose the Yabahar for modeling is, of course, the sound. It's a very intriguing sound, and you're not used to hearing. I can't think of any other acoustical instruments that sound quite like that. And the sound of the Yabahar, like this very reverberant sound, is because of the spring that connects between the string and the drums. And I hadn't seen that before in any other acoustical instruments. And I also hadn't seen like that kind of system exactly being modeled before. So that was why this was an interesting subject to choose.
Cool, thank you. And David, the same question.
Yeah, so I think it came to our attention because it's in the Music Museum in Copenhagen. And the interesting thing about it is that like it used to be quite like a popular folk instrument in Northern European countries, but kind of disappeared somewhat in like the last 100 years or something. But it's still like played in some concentrated regional areas, and that's one of the appeals of physical modeling, that you can kind of like maybe bring historical instruments that are not so available anymore to a little bit of a wider audience. So that was the main motivation there.
Thank you so much. You definitely brought those instruments to the attention of a wider audience. I think that's really great. And I also have a question for our last paper. So there are quite, let's say, there are a few models that are available with the implementation. So do you see a need for kind of making this implementation maybe more modular, or do you see a possibility for it to become more modular? So instead of having just string, plate, and string, plate, could you have some number of strings and plates?
It is actually very modular because I used essentially the same classes of the string and the plate, and then they are just connected together in a different ways, or better, always with a nonlinear connection that is in essence the introduction that Michele brought to this paper from the physical point of view. And so essentially the structure of the plugin is actually very modular. And if in the future, for a future work, I will have to create another plugin with a higher number of subsystems connected together, what I have to do is just use the same classes that I used for this plugin and to connect them together in a different way.
All right, thank you so much. So do we have any more questions, maybe from the audience? Does somebody want to ask something from our presenters? I think there are no more questions. So thank you all for your presentations and for brilliant answers to our questions. And I think this session could be finished a bit early. So we will have probably a bit longer break.